All right, you guys, so this is section 2.5, part 3, algebraic limits. So we've talked about evaluating or estimating the value of a limit both numerically, graphically, and we started talking about some algebraic methods for evaluating limits, but now we're really going to get into evaluating limits algebraically. Your go-to is always going to be to first attempt direct substitution. So just plugging into the function the value that x is approaching. Because if a function is continuous at that point, then the limit of the function will end up matching the point. You do need to be careful. Piecewise functions, it's not really a good idea to do direct substitution, but any other type of function, you'll want to try direct substitution first. That'll be your go-to. So our first example, like I said, we're always going to try direct substitution first. If you run into 0 over 0 or infinity over infinity, those are two different types of indeterminate forms. Where there could be a limit or there might not. And you have to use some algebra to manipulate the function, the expression that represents the function algebraically to get rid of whatever's causing that 0 over 0 or infinity over infinity from the numerator or denominator. So I'm referring to those as being the bad guys that are causing that there to be 0 over 0. That's what we're going to normally run into, like when we try direct substitution and we end up with 0 over 0. That tells us that there's some sort of a common factor that we need to try and get rid of. Okay, so using direct substitution, if we just evaluate cosecant at 5 pi over 3, remember, cosecant is the reciprocal of sine, so this is equal to 1 over sine of 5 pi over 3. And sine of 5 pi over 3 will be, what is that, negative root 3 over 2. So that's 1 over negative root 3 over 2. And when we simplify that, that's just negative 2 over root 3. Which if you rationalize the denominator by multiplying by root 3 over root 3, you would end up with negative 2 root 3 over 3. Okay, so we were able to just use direct substitution there. Okay, so the next limit, we're taking the limit of the square root of negative x as x approaches negative 4 from the left. Remember, this indicates approaching from the left. However, we're still going to just try direct substitution. You guys probably remember this is the square root of x with a horizontal reflection. So the graph looks kind of like that. So as x approaches negative 4 from the left, we're just going to plug in negative 4, which would end up giving us the square root of 4 or 2. Okay, so we can use direct substitution. Unless it's a piecewise, then you kind of need to think about it a little bit more. Think about what the graph is for when you take one-sided limits. Okay. Now we're going to look at when we know there is a vertical asymptote. And when the function has a vertical asymptote, as the function approaches the vertical asymptote, the graph will either increase or decrease without bound, meaning the graph will either approach positive or negative infinity. But you know, if you try direct substitution, you know there's going to be a vertical asymptote at whatever that x value is if you end up with a number besides 0 over 0. So 0 in the denominator but not in the numerator. So like this first example, when we're taking the limit as x approaches 1 from the right, when I try direct substitution, I'm just plugging 1 in. Okay, and when we simplify, we'll get 2 over 0. So that tells me that there is going to be a vertical asymptote at x equals to 1. Which means that the limit doesn't exist, but because this is a one-sided limit, I know that I can either say the limit will be equal to positive or negative infinity to describe why it doesn't exist. So you can figure out what that graph looks like. Excuse me. Or you could think about creating a table of values. Let me grab my calculator out. And if we were to make a table, so what I'm doing right now is just graphing x cubed plus 1 over x minus 1 so that I can create a table. Delete. Okay. So since we want to know what the function is approaching as x approaches 1 from the right, I'm going to choose values to plug into the table that are directly to the right of 1. So like 1, how about like 1.0001, 1.001, maybe like 1.01, okay? So when I plug those in, we know that 1 is undefined. 1.0001 gives me 20,003. 1.001 would give me 2003. And 1.01 it gives me 203.03. So we're thinking about what the function as x approaches, what the function's approaching as x approaches 1 from the right side. So it looks like the values are getting larger and larger as x is approaching 1 from the right. So we can actually say that the limit will be equal to positive infinity. Okay, since it's a one-sided limit. Two-sided limit, you would want to figure out, like if it just said as x approaches 1 and there were no notation indicating from the right or the left, you might want to make a table of values, including values to the left of 1 as well, to see whether or not from the left the graph is approaching positive or negative infinity. Because in that case, if they're different infinities, remember all we can say is d and e. But in this case, the limit doesn't exist because the function is approaching positive infinity as x approaches 1 from the right. Okay, so now we're taking the limit as x approaches pi over 2 from the right of tangent. So again, from the right. Okay, if we try direct substitution, remember tangent is sine over cosine. So you either remember from your unit circle what tangent of pi over 2 is, or you can also think about the fact that tangent is sine over cosine. So sine of pi over 2 would be 1, and then cosine of pi over 2 would be 0. So that indicates that because we got 0 in the denominator and a number in the numerator, that there will be a vertical asymptote at x equals to pi over 2. And because it's a one-sided limit, we need to say which infinity the graph is going to be approaching. So you could think about making a table of values, you could think about graphing. I think that you guys are so familiar with the graph of tangent, or you should be. So I'm just going to do a sketch of tangent. Okay. And then I'm going to put, how about pi over 2, pi, 3 pi over 2, 2 pi, I'll go negative pi over 2. Because if you remember, there's going to be a vertical asymptote. Well, we know there's a vertical asymptote at pi over 2, but there's also a vertical asymptote at 3 pi over 2 and negative pi over 2. And then the graph is the S shape. Where the fundamental period for tangent is pi. So we can see that as x is approaching pi over 2 from the right side, it looks like the graph is approaching negative infinity. So we'll say that this limit is equal to negative infinity. Doesn't exist, but we can say that it doesn't exist because the function approaches negative infinity as x approaches pi over 2 from the right. All right, limits at infinity we've already studied. Okay, so we're kind of going through some different examples that are review. So remember, for taking a limit as x approaches positive infinity of a rational function, right? This is a ratio of two polynomials. You're going to determine what the end behavior model is. So the end behavior model for this function will be the ratio of 5x squared over negative 4x squared, and that's because those terms, 5x squared will dominate the other terms in the numerator as x gets infinitely large, and negative 4x squared will dominate the other term in the denominator as x gets infinitely large. So we can see that the x squareds cancel, leaving us with negative 5/4. So that's just a horizontal line. So now, when we think about taking the limit as x approaches infinity of this kind of complicated rational function, we know that this rational function has the same end behavior as the horizontal line y equals to negative 5/4. So therefore, this limit will be equal to negative 5/4. And by just as an extra, so the limit is equal to negative 5/4, but just as kind of an extra piece of information, remember by definition, you also know there's a horizontal asymptote at y equals to negative 5/4. Okay. Next example. Again, a rational function as x approaches negative infinity. So I'm going to determine the end behavior model from the ratio of the terms that have the largest exponents. Okay, that'll simplify to be negative 2x squared. So this is interesting. We ended up with a quadratic as our end behavior model, and it's a quadratic that has a leading coefficient of negative 2. So that's a quadratic, or a parabola, right, is the graph of a quadratic that opens down. Meaning, as x approaches negative infinity for this function, that function is going to have the same end behavior as y equals to negative 2x squared, meaning the function will end up approaching negative infinity. Okay. So let's look at how we deal with limits of piecewise defined functions. Okay, so if we're taking the limit as, let me pick another color. We're taking the limit as x approaches 2. This is asking for the two-sided limit. We can see that for this piecewise, 2 is the endpoint of the intervals for which each piece is defined on. So I'm going to think about taking the one-sided limits here. So I'm going to take the limit as x approaches 1 from the left, not 1, 2. As x approaches 2 from the left of f of x, and I'm also going to take the limit as x approaches 2 from the right of f of x. And remember, if the one-sided limits both exist and agree, then we'll have our limit. If they do not agree, then the limit will not exist. So when we're taking the limit as x approaches 2 from the left, this first interval, x less than or equal to 2, will have values directly to the left of 2. So we can think about plugging 2 or using direct substitution into the first piece of the piecewise. So 4 minus 3 gives us 1. Okay. And then for this function, as x approaches 2 from the right, since 2 is an endpoint of the interval, or where the function switches, the domain restrictions switch, values directly to the right of 2 will be in this second interval. So we'll use direct substitution into the second piece of the piecewise. So 1 plus 1 equals to 2. So in this case, the one-sided limits both existed, like we got a limit for each of the one-sided limits. However, because they are not equal, all we can say about this limit is DNE. You could have also sketched the graph, but sometimes depending on what the pieces are of the piecewise, it might be easier to just use direct substitution and look at what the intervals are that each piece is defined on to see where you would be plugging the value in. All right. This next piecewise, we're taking the limit as x approaches pi. Now, this function says that when x is not equal to pi, the function is going to look like sine of x. And when x is equal to pi, then we'll have the point pi comma 1. So let's think about this. Basically, as x approaches pi from the left and the right, we would be plugging values into the first piece here. Because we do know what this looks like, I'm going to give you the visual by graphing. And then hopefully that'll make more sense about why I'm going to say that you can actually use direct substitution by just plugging pi into the first piece here. So let's do pi over 2, pi, 3 pi over 2, 2 pi. Okay, x, y. Oh, and then remember, sine oscillates between 1 and -1. I'm going to leave an open circle at pi comma 0, because sine of pi is 0. Thinking back to your unit circle, which I know you all remember. And then for this piecewise, when x is equal to pi, the function is equal to 1. So f of pi is equal to 1. So there's a point up here. Okay, so we can see that as x approaches pi from the left and from the right, it looks like the function is approaching 0. Meaning, since the function is going to look like sine of x everywhere except for at that one x value that we're taking limit as x is approaching, we can actually just use direct substitution and substitute pi into that first piece, and that'll give us 0. That's where piecewise functions are a little trickier. You do need to kind of think about the domain restrictions of each piece, and sometimes if you're able to visualize what the graph is, that could be helpful too. But they maybe just take an extra step of thinking for whether or not you can use or how to use direct substitution. All right, and everybody's favorite, squeeze theorem. So remember, you guys have the steps that I would like you to follow. And a good indicator that this is a squeeze theorem problem is the fact that I give you the function, the inequality that represents the relationship between these three functions. So I'm asking you to take the limit as x approaches 1 of f of x, and I've given you that if f of x is greater than or equal to ln of x plus x squared and less than or equal to e to the x minus 1 for all x in an interval containing x equals to 1, except possibly at x equals to 1 itself, right? Because f doesn't necessarily need to be defined at x equals to 1. Then we're going to find the limit. So remember, our first step is just going to be to state the relationship. So the fact that I've given, why am I writing limit? The fact that I've given you the inequality already makes it really easy. Okay, and then the second step is going to be to show the limits of the outside function. And you can either write that separately, or if you want to show taking the limit of each piece of the inequality, that can work too. But you need to first make sure you're stating the relationship between the three functions. Okay. So then I'm going to use direct substitution for the function on the left to evaluate that limit. So ln of 1 plus 1 squared and then the function on the right. So ln of 1 is 0, right? Because e to the 0th power, it would give you 1. And then 0 plus 1 squared would just be 1. And then e to the 0th power will also be 1. So that means that by the squeeze theorem, the limit as x approaches 1 of f of x has to be equal to 1. Done. So just follow those 3 steps. That's your justification for what that limit is. All right, so the rest of the methods below deal with the algebraic methods used to eradicate the 0 over 0 or infinity over infinity from the expression. So that direct substitution may be used. Okay, so I have these little names. I did not make them up. I got them from another teacher, but I have these names to try and help you guys remember the different methods. You don't have to have them memorized. It's just important that you recognize what method to try when you run into the 0 over 0 or infinity over infinity case. We've already done this first method. So remember, if we try direct substitution, you could see that we would end up with 0 over 0, that indeterminate form. So I'm going to try FODO, factor and divide out, since this is a rational function, right? Ratio of 2 polynomials. I'm going to factor the numerator, which is a difference of 2 squares. Okay, and then I can see that those x minus 2's are what's causing the 0 over 0. And I would know that, actually. Like, if you couldn't figure out what that factored to, you know that x minus 2 is going to have to be the common factor in the numerator and denominator, since you ended up with 0 over 0. So this will be the limit as x approaches 2 of x plus 2. And then now we're ready to try direct substitution again, and we end up with 4. Okay. So again, if you try direct substitution, you end up with 0 over 0. So we need to factor, and you either remember what a difference of 2 cubes factors to. If you had Mrs. S for algebra, you probably remember that. But you also know that there's one factor that's a common factor that's causing the 0 over 0. And since when we substitute 1 in, we're getting 0 over 0, x minus 1 has to be that common factor. So if you want to figure out what times x minus 1 would give you the x cubed minus 1, you could always use polynomial long division, or you could also use synthetic division. But since we've already used polynomial long division, because you're trying to figure out what times x minus 1 would give you x cubed minus 1. Since we've already done polynomial long division for finding slant asymptotes, I'm just going to use polynomial long division. Good practice. Make sure that you put the placeholders in there. So 0x squared plus 0x minus 1. So we go, what times x would give us x cubed? That'll be x squared. And then, oh no, what am I doing? That'll be minus x squared, sorry. When I think about distributing the x squared to x minus 1. Okay. And then I can subtract. That'll give me x squared, and I can bring down the 0x. So what times x would give me x squared? That'll be plus x. Distribute. Subtract. Bring down the minus 1. So that'll be plus 1. And we can see we end up with the remainder of 0, which makes sense because we know that x minus 1 is a factor of x cubed minus 1. So x minus 1 times x squared plus x plus 1 gives us x cubed minus 1. And now we can see that the x minus 1's will cancel, leaving us with the limit as x approaches 1 of x squared plus x plus 1. We got rid of what was causing the 0 over 0, so now using direct substitution, we get 3. Okay. For this one, we try direct substitution. You're going to end up with 0 over 0, which tells me that x plus 1 is a common factor in the numerator and denominator. And then I need to figure out what the other factors are in the numerator and denominator. Denominator is easy because that's a quadratic. So what, that'll be 2x, x plus 1 times 2x minus 3. Yeah, would give me 2x squared minus x minus 3. And again, we can do polynomial long division. I don't really have room over there, so I'm going to do x plus 1. Or sorry, x to the 4th minus x cubed minus x squared minus 3x minus 4, no placeholders needed, divided by x plus 1. So what, it'll be x cubed times x gives me x to the 4th. Okay, subtract. Bring the minus x squared down. Minus 2x squared times x would give me negative 2x cubed. Multiply and subtract. that gives me x squared. Bring the minus 3x down. So x times x gives me x squared. Subtract. And you guys know that if you get a remainder other than 0, something went wrong. Okay, because we know that x plus 1 has to be a factor of the polynomial in the numerator, since we ended up with 0 when we plugged -1 in. Okay, so x plus 1 times x cubed minus 2x squared plus x minus 4 gives us that original polynomial in the numerator. We can now see that the x plus 1's will cancel, leaving us with the limit. And I'm expecting you guys to show your work using the proper limit notation. So it leaves us with x cubed minus 2x squared plus x minus 4 over 2x minus 3. And now we can try direct substitution. And I believe we end up with 8/5. Okay, so that's FOTO, factor and divide out. So when you have a rational function, a ratio of two polynomials, and you run into 0 over 0, factor and divide out what's causing the 0 over 0. All right, RATCON. Short for rationalization and conjugation. Okay. So this is for when you run into the 0 over 0 case when applying direct substitution. And you have some work to do to get rid of what's causing the 0 over 0. So we could see that if we plug 0 over 0 in for x in this first example, that we would end up with 0 over 0. So what I'm going to do is I'm going to try and rationalize the numerator by multiplying by the conjugate. And the conjugate of the numerator would be the square root of x plus 1 over itself, right? That's the same thing as multiplying by a version of 1, which you're allowed to do. It might be helpful to put parentheses just to remind yourself that the division bar is a grouping symbol. So when you multiply this out, root x plus 1 times root x plus 1 is just x plus 1. Then 1 times root x plus 1. I'll write it out for this first one, but I'm going to skip this step for the next ones. So we'll have 1 times root x plus 1 is root x plus 1. And then -1 times root x plus 1 will be minus root x plus 1. And then -1 times 1 will be 1. So we can see that the root x plus 1's end up canceling. And that'll happen every time. That's why we're able to rationalize. And then I'm going to leave the denominator factored. Okay, so combining like terms in the numerator, I'll get x plus, oh, that was, sorry you guys, that was minus 1 up here, huh? When I did -1 times 1. So the 1's end up canceling, and then I'll be left with x in the numerator. The denominator is still the same thing. But you can see that the x's will cancel. And those are what were causing the 0 over 0. So the limit as x approaches infinity of 1 over root x plus 1, where now we can use direct substitution. I'm going to resize this so it fits a little better. Make one more attempt. Okay, we're just going to go with it. So now when I try direct substitution, I'll have 1 over the square root of 0 plus 1 plus 1. That just simplifies to be 1/2. So that limit as x approaches 0 is 1/2. Okay, next example, if we try direct substitution, we'll get 0 over 0. You can either write out the direct substitution or you can do it in your head. So, because I see those radicals, I'm going to try ratcon. So I'm going to rationalize, in this case, the denominator. Oops. By multiplying by its conjugate, which will be root x plus 2 plus root 5 over itself. Okay, because I'm trying to rationalize the denominator, I'm going to leave the numerator factored. And I can see that x minus 3 is what's causing the 0 in the numerator. So when I leave that out to get it to cancel. So when I distribute, that's going to be x plus 2. The root 5 times root x plus 2 will cancel with the negative root 5 times root x plus 2. And then negative root 5 times root 5 will be just minus 5. Okay, so we'll have x minus 3 times root x plus 2 plus root 5 over x minus 3. And yep, you can see the x minus 3's can cancel. And we're left with the limit as x approaches 3 of root x plus 2 plus root 5, where now we can try direct substitution again. And that ends up being root 5 plus root 5, which is 2 root 5. Okay, so 2 root 5 is our limit. Okay, so these next examples you're going to see are when you have a complex fraction, so a function that has a complex fraction, so like a fraction in the numerator or denominator or both. And when you run into, if direct substitution leads you to 0 over 0 in determinate form, you're going to attempt to get rid of the complex fractions by multiplying by the least common multiple of the denominators of the complex fractions over itself. So in this case, and you should be writing out your steps, the algebra steps, just like I am, inside the limit notation. You should have the limit notation until you use direct substitution. Okay, so the least common multiple of x plus 2 and 2 will be 2 times x plus 2. Or 2 times the quantity x plus 2, I should say, over itself. Remember, division bar is a grouping symbol. So when we distribute this product to the first fraction, the x plus 2's cancel and we're left with 2. And then when we distribute to the second fraction here, the 2's cancel and we'll be left with minus the quantity x plus 2. And then the denominator will be x times 2 times x plus 2. Distribute the negative and combine like terms so that you can see the numerator ends up being negative x over x times 2 times x plus 2. So the x's, which that makes sense, right? If 0 was what was causing, when we plugged in 0, we end up with 0 over 0. That makes sense that we would have the x's canceling. So that's negative 1 over 2 times x plus 2. You can use direct substitution now. So we get negative 1/4. I'm going to go to the right just because I'm running out of room. So negative 1/4 for that limit. Okay. Next limit is of a function that has complex fractions in the denominator. You run into 0 over 0. I know that I should, because I'm plugging in 0 and getting 0 over 0 in the denominator, once I have multiplied by LCM over LCM, I should end up with an x that cancels with that x in the numerator. So we're taking the limit as x approaches 0, just rewriting the original function. And I'm going to multiply by the least common multiple of the denominators of the complex fractions, which will be 6 times x minus 6 over 6 times x minus 6. So smallest common denominator, what I'm describing is finding the smallest common denominator of the complex fractions. Okay, the numerator will be x times 6 times x minus 6. I'm leaving that factored because I know I want that x to cancel. Remember, division bar is a grouping symbol, so I'm distributing that product over to the 1/6, where the 6's will cancel, and I'll be left with just the quantity x minus 6. And then I'll distribute to the next fraction, and the x minus 6's will cancel, leaving me with plus 6. If I combine like terms in the denominator, I apologize, my allergies are crazy right now. X's cancel, so we get rid of the bad guy that's causing that 0 over 0 with direct substitution. So now we can think about taking the limit as x approaches 0 of 6 times x minus 6. So use direct substitution. Once I use direct substitution, I can drop the limit notation. So I get negative 36 as our limit. All right, almost done. Now the least fun form of evaluating a function algebraically. So when you run into the 0 over 0 case and there's no obvious algebra to do, no retcon, no FODO, you just have to expand. So multiply everything out. I call this the sledgehammer method. Okay, so using brute force, we are going to just multiply everything out, right? Looking at this function, it's not obvious to anything else to do. Because we're taking the limit as h approaches 0, and I see that there's an h in the denominator that right when you use direct substitution is 0, that means I'm going to try and get an h in the numerator that I can have cancel with that h in the denominator. So I'm just going to think about multiplying out the numerator and combining like terms. Okay, so the numerator will be x squared. That'll be plus 2xh plus h squared. Right, that's just applying the distributive property multiple times. Now when I combine like terms, you should see that the x squareds will cancel. That leaves me with 2xh plus h squared over h, which I'm going to actually factor an h out from that. I'm just going to do it in the same step. So now the h's will cancel. And when I use direct substitution, I'm just left with 2x. Okay, and yes, I'm left with a function. You'll see this type of limit is going to lead into what we're studying next. But the limit in this case ends up being 2x. Oh man, this is yucky looking. So again, not really much you can see that you could use. Up here we ended up with 0 over 0. Same thing down here. If we plug 0 in for all the h's, you'll get 0 over 0. So the only thing we can do is multiply everything out. When I distribute that -2, plus 1, and then I'm going to distribute the negative. Oh, this is yucky. And you know what? I already multiplied that. I already multiplied this out above. I know what that is. X squared plus 2xh plus h squared. Just save myself a little time. All right, let's look at what cancels. I'm going to cross things out. X squareds cancel, 2x's cancel, the 1's cancel. And then notice what I'm left with in the numerator all has an h. Or each term has an h. So I'm going to factor an h out. So that what was causing the 0 over 0 can cancel. And we'll take the limit as h approaches 0 of 2x plus h minus 2. Now trying direct substitution, we just get 2x minus 2. Okay. Sometimes, so this does not cover, these are kind of common cases that will come up using FODO, RATCON, LCM over LCM. But remember, you're always going to try direct substitution first. Sometimes though, there's functions that it ends up being like a combination of strategies, or you might even have to apply some of the limit properties. But we're just going to start with this where you use these common strategies.